Start with questions from the homeworks. Anybody got anything from last time? 1 through 15, I think, is what was assigned. 12, sure. Okay, so it says to find the zeros algebraically. So what do we start by doing? Set it equal to 0. Yep. Okay. The next thing we'd want to do is greatest common factor of x. Very good. Oops. X. Now we can apply the zero product property. And clearly x equals 0. But the other piece that we have is this quadratic. How do I solve a quadratic that looks like that? Anybody? We just did this yesterday. Try to factor this, right? What question do I need to answer in order to factor this? The two numbers that multiply to give me what and add to give me what? Multiply to give me and add to give me half right. That's good. And 15 is almost right. Yeah, it's 15 times 3. Why is it times 3? That leading coefficient is not 1. Remember that what we had used last time was always the shortcut because the leading coefficient was always equal to 1 in those cases. So you didn't have to worry about it. But if it's not 1, in general, that's the process. Okay, so what multiplies to give me 45 and adds to give me 14? Go through your times tables for 45. Anybody see yet? 9 and 5, there you go. Now, here's the catch, though. 9 and 5 don't take me to the factors. What 9 and 5 do in this situation is just tell me how to break apart that 14x. Hi. Ruthie. Looks like you're going somewhere early. Sure. You're welcome. So far, so good. I'm now going to make two groups. Very important when I make those two groups that the symbol in between them must be addition. What if I had a subtraction symbol there? What would I have to do? I'd write it as plus a negative. Right? Easy fix, but you got to remember to do it. Okay. Now that we've rewritten this in a factored form, or in two groups, I'm going to take a greatest common factor from the first group. So what do I have in common between 3x squared and 9x? 3x. What's left after I factor the 3x off? Excellent. And then 5x and 15. And what's left? X plus 3. If these two factors aren't the same, it's likely you've made a mistake somewhere along the way. They should always be the same, because the final step, I look at this as one whole thing, and I look for a greatest common factor between each term, which is clearly the x plus 3. And what's left is the 3x plus 5. So now I can solve this to get x equals 3 and x equals negative 5/3. Now, what did you notice about the factoring this time than what we did yesterday? A lot more time consuming, wasn't it? This is a lot of extra steps, there's a lot of extra work. Is there a way to solve this without having to factor it? What else could have we done? I could just use the quadratic formula, right? So if I wanted to do that, well, what's 14 squared again? Is that 196? I think it's got to be, right? Yeah. So 14 squared is 196. And 4 times 15 times 3 is 180. 196 minus 180 is 16, and the square root of 16 is 4. So negative 14 plus 4 is negative 10 over 6, or negative 5/3. And negative 14 minus 4 is negative 18 over 6, which is negative 3. Notice those are the same results that we got below. If you prefer to do that rather than going through the rigmarole of factoring it, that's certainly an acceptable method as well. Does that feel good, Lucas? I got it right today. I'm up to maybe 50% now. I don't know why it's so hard. Too many Millennics. Ava. Yeah, same section, I think, right? So again, we start the same way. Now there's no greatest common factor. Everybody agree? So I can either try to factor this. If I do that, I have to do the long method that we just did for the previous problem. Or I could use the quadratic formula. Which would you like to do? Okay. So I have x equals negative b plus or minus b squared minus 4ac all over 2 times a. So that's 1 minus 20, or minus a negative 24. So negative 1 plus, or negative, or 1 minus a negative 24 is 25, square root of 25 is 5. So negative 1 plus 5 is 4 over 4, which is 1. And negative 1 minus 5 is negative 6 over 4, which is negative 3 over 2. You could have also factored that. That would factor also, but This is what I would do. When I see a leading coefficient that's not 1, that I can't get rid of that leading coefficient via factoring, a greatest common factor, I'm just going to quadratic formula it. To me, it's faster. Certainly less space. Feels like less space. One like this, I might actually guess and check the factoring and just be like, okay, I know 2x, 2x and then 1x, and I know there's, one of them's a -1 or a +1, the other's a -3 or a +3, so there's really just 4 combinations to check. That wouldn't be bad to do either. But I don't want to do the long factoring on it. Yuck. Anybody else? Cheyenne. 14? Oh, yeah, sure. Okay. So if I know that my function has the zeros of √5, -√5, and 1, I know that those are also solutions to the equation like f of x equals 0, right? Does that feel okay? So what I'm going to do is each one of those solutions, I'm going to subtract, I'm going to move everything onto one side so that they're equal to 0. Which is all fine, right? Okay. Now I'm going to take each one of these and I'm going to multiply their left-hand sides together. And I'll multiply their right-hand sides together, which is just going to be 0 times 0 times 0, or 0. So far, so good? Okay. I'm now going to multiply this stuff out. So I'm going to start by multiplying these two parts together that both have the radicals in there. I notice when doing that this is a difference of 2 squares factoring pattern. I have like an a minus b times an a plus b. So when I FOIL that out, I know I'm just going to get a squared minus b squared. And what's square root 5 squared? Just 5. Yep. So now I'm just going to keep on foiling. So I'm going to get x cubed minus x squared minus 5x plus 5 equals 0. And I am donezos. I guess it doesn't need to equal 0. That could just be f of x or whatever, but we got the polynomial out of it, right? That's the point. So last time we had like no heat. Today we have too much heat. I don't know what the deal is. I emailed maintenance. It's dumb. Is this now the hottest room in the school, you think?
No, that's an expensive place.
Really? It says it's like 78 or something in here right now on the thermostat. Woo! Okay. You guys ready to start the new stuff then? Okay. Let's do that. So we're going to do 13.3 today. Before we start, though, I want to go back and retouch a topic from elementary school. So put on your time travel clothes and step into your time machine. We're going to go back to practicing some long division. Somebody quick, give me a 4-digit number. 5,723, okay. And then a 2-digit number. 14. Great. You guys are much more G-rated than the PG-rated previous class. Any guesses though your 2-digit number I heard first? Yeah, you got it. Ha 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 ha. I kicked myself as soon as I said it. I'm like, I should know better than that. All right. So you guys go back and tell me how we set up a problem like this to do via long division. Yep. So we build our little division bar here or whatever. And the 5,723 goes under. What goes on the outside? 14. Okay. So that's my setup, right? You guys remember doing this? What do we do next? Okay. How many times does 14 go into 57? 3 times. Yep. So 3 times 14 is, no, I think it goes 4 times, right? That's 56. We subtract down. 14 doesn't go into 12 any times. I think it's 8. I don't think it's 9 because 9 times 4 is 36, and that's going to be 90 plus 36 is 126, so it's too big. It's 8. So that's 80 plus 32, so 112. Everybody's okay with that? So the way we'd write our answer then is we say that like 5,723 divided by 14 is equal to 408 plus 11 over 14. Little quick piece of vocab here. What do we call that number 5,723? What part of the division problem is that called? That's the dividend. What's the 14 called? Divisor. Good. And the 408 is the quotient. And the 11 is remainder. And then the 14 again was the divisor. So every division problem can be written as dividend divided by divisor equals quotient plus remainder over divisor. Is that okay with everybody? That jogs our memory a little bit as to how long division works. Okay. What if we want to do that with polynomials? Say we want to use long division to rewrite 2x cubed minus 4x squared plus 5x plus 1 divided by x squared minus 3 in that same quotient plus remainder over divisor form. Well, we set up the same way, right? So the dividend goes underneath and then the divisor goes outside. Everybody like what I did here? This is not how I would write it. Look at that divisor. Are you missing anything there, Matt?
X minus 3, like in parentheses, x squared, so it's like
Not that. But look at that x squared minus 3. There is something that I would change to that. Are we missing anything there? X squared and then minus 3. What are we missing there? We don't have any x term, right? So the way I would write this is I would write it x squared plus 0x minus 3. Now, is it critically important that I put that 0x there? No. The problem is still recoverable if you don't do that. What's going to happen if you don't do that, though? The like terms aren't going to line up automatically for you, and it's going to be a hassle and going to make it very easy to make a silly mistake like adding x squareds and x cubes or something. We don't want to do that. My recommendation is anytime you have a skipped term, make darn well sure you write the 0 in. Everybody's good? So far, so good? All right. So our setup, I'm going to start by saying what times x squared gives me 2x cubed. 2x. So I'll write that here. And then that's going to multiply the entire divisor. I'll write the result underneath. And then subtract. The number one place where I see students make mistakes in doing this process is screwing up the subtraction. My suggestion to you is turn this into addition of a negative. How do I do that? I distribute the negative through. And now I can just add straight down. I don't have to worry about anything else. Everybody's cool? Okay, next step. What times x squared gives me negative 4x squared? Negative 4, right? So once again, multiplies to the entire divisor. And then I subtract down. Before I start subtract, or how do I do the subtraction? Adding the negative, so I'm going to distribute the negative through. So that's my remainder. So now I just need to write my final answer. Hi.
Hi.
Welcome. So we have this fraction is equal to the quotient plus the remainder over the divisor. Did you guys kind of remember doing this last year? Yes. Good. Okay. So, one of the important pieces that follows as a consequence from polynomial division is the remainder theorem. It states that if you have some polynomial f of x and we divide by some monic polynomial x minus k, the remainder is the same thing as f of k. So let's look at an example. Here it says find f of 2 using the remainder theorem for this f of x. Everybody's okay with that? So what that means then is I'm going to be using x minus 2 to divide f of x. So there's my setup. So what times x gives me 2x squared? 2x. Multiply through 2x squared minus 4x, and then I'll subtract through. Then I'll ask myself, what times x gives me x? 1. Multiply through. And we'll subtract down. And I get my remainder as 6. So that tells me f of 2 should equal 6. Yes?
How did you get the x minus 2 that's on the outside?
I multiplied 1 to x. Oh. Because k is 2, so that tells me that I'm dividing by x minus 2. Right, what does the theorem say? Oh boy, hold still. If f of x is divided, I guess that says, should be past tense, by x minus k, then the remainder is f of k. So the fact that I had a 2 here tells me k is 2, tells me that x minus 2 should be my divisor. Elise?
I'm not understanding the 1. I understand the 2x, but
So I wanted to ask myself, what times x gives me x? So then I subtracted, yes. So I distributed the negative through, and that's why I wrote it as negative and plus. Yep, exactly right. Sophia? Yes. Ava?
when you subtracted, like you get x plus 4, shouldn't that have been negative x plus 4?
Oh my goodness. Yeah. Why didn't you notice that earlier? It's okay. Thanks. Try to keep the edits to a minimum, but at least we'll do them in purple so it's easy to see them now. All right. So that's doesn't seem that helpful though, because what would have been easier to figure out f of 2 by doing? Can I just plug 2 into this? And that seemed like that's easier. Here's where it would be more helpful. What if I wanted to go this direction? What if I ask this problem? Like, what is the remainder if I do f of x divided by 2? Or divided by x minus 2? There, I can just do f of 2. And boy, that seems a lot easier. Everybody okay with what we did there? So again, you can use that theorem kind of going either direction. Now, if we think about what we've been trying to do most of this chapter so far, we've been largely doing factoring and solving, right? Everybody agree with that? That's kind of been the big overarching goal, has been looking for these zeros for functions, which I'm going to get by solving equal to 0. And to do that solving, really writing things in factored form becomes kind of a necessity, right? So if we think about this process of division, what remainder value is going to be the most informative for us if we're trying to eventually get to factoring and solving? What numeric remainder is going to be the most informative to us? Anybody want to venture a guess? If I have 8 divided by 2, what's the remainder? Come on, guys. 8 divided by 2, what's the remainder? 0, right? There is no remainder. And what does that tell us about 4 and 8? Tells us that 4 is a factor of 8. That's the remainder value that we're going to be most interested in, is when the remainder is 0, because that indicates to you whatever the divisor was is a factor of that polynomial. So that's what we're going to call the factor theorem. Says that f of x has a factor x minus k if and only if f of k equals 0. So let's say we have this example. We want to show that x plus 3 is a factor of 6x cubed plus 25x squared plus 16x minus 15. Well, what is the k going to be in this case? -3, very good. So all I need to do is show that f of -3 is equal to 0, right? Well, f of -3 is 6 times -3 to the third plus 25 times -3 squared plus 16 times -3 minus 15. Let's see, what's that? 162 minus 225 minus 48 minus 15, and that is 0. Yes, sure. So what have we done there? We've shown that 6x cubed plus 25x squared plus 16x minus 15 is going to equal to x plus 3 times something else, right? But we don't know what that something is. Everybody agree? We know that this x plus 3 is a factor, but we don't know what times x plus 3 is going to give us that. What are we going to have to do to get that other half of our factor, or that other factor? What's the other way that we could use to do this? What other process is going to give us that information that the remainder is 0, but also tell us what that other half of our factoring problem is? It's polynomial division. Oh, boogers. That's I'm sorry, this is negative, that's positive. Thanks, Cheyenne. So that quotient from our polynomial division is going to give us the result. Well, I have the parenthesis around the whole thing. I just didn't just do the distribute because I'm just going quick now. We've done our examples of doing this, so I just wanted to kind of like gun through this process here because practicing the division isn't the point. It's getting that remainder out of there, or getting that quotient out of there, excuse me. So notice both of these two processes tell you the same thing. They're both going to be effective ways to show that the remainder for this division problem is 0. The factor theorem has the catch that it doesn't actually tell you how to do the factoring, though. The polynomial division takes a lot longer, but it has the added benefit of giving you the factors with it. What would be nice is if we could combine these two processes together so to have something that's easy like the substitution, but still gives me all the same information as the long division, right? That's what we'd want. Because the long division kind of stinks. It takes that's a lot of effort. Well, there is a process that does that. It's called synthetic division. But there is a catch. Does anybody remember the catch with synthetic division? I think you did this last year. You can't use it every time.
I try.
So this is synthetic division is only going to work when your divisor has degree equal to 1 and leading coefficient equal to 1. Basically, it looks like an x minus k. We have a special name for those kind of polynomials. We call them monic. I'll use that terminology here and there, but that's all it means, is something that looks like x minus k. All right, let's run through this synthetic division process. Again, I think this was something you guys did last year, right? But it's been a minute, so let's run through this to make sure we still got it. So I'm going to start by drawing in my synthetic division bar. What number is going to go out here? I'm going to take my divisor, set it equal to 0, and solve. Everybody's okay with that? What numbers am I going to put in here? I'm going to use the coefficients from my dividend. Now, what do I have to be especially careful about when I'm writing those in? Does anybody remember? I have to be especially careful that if I'm missing any terms, that I put a 0 there. Now that didn't happen in this case, right? I didn't need to worry about including a 0. But unlike polynomial long division, where you can still recover if you don't include a 0 if you're careful, here, if you don't put a 0 in, there is no recovery. You can't careful your way through it. You're going to just get it wrong, and it's not going to work the way you need it to. Have to include the zeros if you're missing a term. Everybody's clear? Okay. Do you remember how this starts, what the first step is? Start just by bringing down the first number. And then we take the number on the outside, multiply it to the number on the bottom, write it in the next spot, and add down. And then we just repeat this process till we've filled out the rest of our spots. And somehow, if you know how to read these numbers at the bottom, this is going to tell me everything that I need to know from the same information as that long division problem. This was much faster, much simpler, took much less space, The arithmetic was much easier, much harder to make a negative mistake or combining like terms mistake, because it's just numbers. There's no variables anymore. This was nice. So here's how we interpret this. These numbers at the bottom are all we need to know. We read these numbers from right to left. This is like the only time in your life that we're going to be reading things from right to left in mathematics. The number on the furthest right is your remainder. Matt? Yeah. The next numbers are constant term, our x coefficient, and our x squared coefficient. So because the remainder was 0, that tells us that x plus 3 is a factor of our dividend, excuse me. Everybody's okay there? And these numbers tell us the other factor that we were missing. So in this way, this synthetic division gives us everything that we would get from long division, including the factoring part. It gives us both factors. Yes. Yes. Because I don't like long division. It's a real pain in the tuchus. What's the only downside of synthetic division? Doesn't work every time. Exactly right. All right. So how else can we use synthetic division then? Well, you could use it to do something like this. You can use synthetic division to evaluate f of -5. Now remember that if we ask you for f of -5, this means the same thing, right? Or we can set this up as a synthetic division problem. What number is going to go on the outside here? Not 5, -5. Because remember, this is f of k. So -5 is the k. And then what are the numbers that go on the inside? 4. Then what? Not -5. We've gone to x to the 4th, and then we have an x squared. What did we skip? Yeah, we need a 0 there. And then we can do -5, 7, -8. Everybody feel good here on the setup? Whoa, that was scary. Stompy McStomperson's out there, huh? -475. And then what's that? 2340. Which would be the same thing that we get if we did it that way also. Everybody okay here? So we've seen that we can use synthetic division to do factoring, right? If we know what the factors are, or at least one factor, we can divide that factor off and get another piece and potentially do some more factoring on that piece and keep on going, right? What's the hanging question here? How do I find a factor to start this synthetic division with? Right? That's what we're going to be talking about for the rest of the lesson here is, okay, I can use a synthetic division to do factoring, like we saw up here in this example. But in that example, we're told that x plus 3 was a factor. What if we're not given that piece? How can we figure out, like, what are potential factors? What should I start my synthetic division with? So we'll start with something called the rational roots theorem. It says for a polynomial f of x, the only rational root, or I should say zeros, of f of x are of the form p divided by q, where p is a factor of the constant term and q is a factor of the leading coefficient, which I abbreviated LC. Yes? Sure. When we say rational in mathematics, what do we mean? Do we mean logical? Like, oh, that was a rational decision you just made. No. What do we mean? We mean that it's a rational number. It's a number that could be written as a fraction. Okay? So keep that in mind. So let's do a quick example using this rational roots theorem, because this is going to be one of our main tools for deciding where to start our synthetic divisioning. All right, so it says make a list of every possible rational zero for the polynomial 3x to the fourth plus 4x squared plus 7x minus 4. So I'm going to start by just identifying my constant term. I'm just going to abbreviate that CT, and my leading coefficient. What's my constant term? -4. What's the leading coefficient? 3. What are all the factors of -4? Or another way of asking this, what are all the numbers that divide -4 evenly? How about 1 and -1, right? 2 and -2, 4 and -4. That's it. What are the factors of 3? plus or minus 1 and plus or minus 3. So these guys are like my P's, and those are like my Q's. So my possible rational zeros are going to be all my combinations of P divided by all combinations of Q. So I'd have plus or minus 1 over 1. Let's write it this way. Plus or minus 2 over 1, plus or minus 4 over 1, and then plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 4 over 3. Now, those first three, is that really going to be the way I write those? Probably not, right? What am I going to call 1 over 1? Just 1. 2 over 2, I'll just write 2. 4 over 1, just write 4. Everybody's okay with that? So that's how we use the rational roots theorem. We'll circle back to that in a second. There's another theorem that's going to be helpful to us. And I'm going to just screen grab this because it's kind of long. And it's just too much writing for me. Well, or you can, I mean, I'm giving you all my notes, right? Like, you don't really have to write anything because you have all of this. I mean, you just have to be able to use it. You don't have to, I'm not going to ask you to like write down blah, 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 blah. You know, like you have to know it enough to use it. You don't have to write it. You know what I mean? Like, what a boring math class that would be. Like, write down blah, 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 blah. Like, here, write this theorem down. Ugh. Just like all memorization.
Yeah, that was honors geometry freshman.
Yeah. All right. So this says if f of x is a polynomial with positive leading coefficient, and we divide by x minus k using synthetic division, if that k is non-negative, every number on the bottom line and every number on the bottom line of the synthetic division result is non-negative, then k is an upper bound for all the real zeros of f. Upper bound means that it is all the real zeros then would have to be less than or equal to that number. Likewise, if k is non-positive and every number on the bottom line of the synthetic division is alternatingly from non-negative to non-positive, then k is a lower bound for all the real zeros of f. Again, that means it is all the actual zeros are greater than or equal to that number. So what we can do with this is a problem like this, where we can show that all of the zeros for a polynomial lie within some specific interval. It's not actually going to tell you what the zeros are, but instead of the zeros being able to be anywhere, we know that they'd have to be between -5 and 4 in this case. So what do we need to do? We need to show that -5 is a lower bound and 4 is an upper bound. Everybody's cool with that? So to do that, I'm just going to do synthetic division. And look at the result. So here, let's see what I have. My first number is greater than or equal to 0. then I have less than or equal to 0, greater than or equal to 0, less than or equal to 0. So for my lower bound, every number in the bottom line alternates from non-negative to non-positive. That is what I see. So that I know that -5 then is a lower bound for the zeros of f of x, or I know that all the zeros of f of x are greater than or equal to -5. Either way of saying that is fine. Then we'll do the same thing. We're just going to go ahead and do synthetic division again, but this time we're going to use k equals 4. Here I notice that every number below my synthetic division is greater than or equal to 0. That's what we're supposed to have. So we know that 4 is a upper bound for the zeros of f of x, or that is that the zeros have to be less than or equal to 4. And if we take these two things together, the fact that zeros have to be less than or equal to 5, or I'm sorry, greater than or equal to -5, but less than or equal to 4, that tells us that the zeros are on the interval from -5 to 4. Is that okay with everybody? Now, there's a show question. They're not going to get like a number result. And in fact, we're not even going to tell you what the zeros are from this. All we can tell you is, hey, they live in here somewhere. But that's a heck of a lot better than them being anywhere from -infinity to +infinity, as we've really narrowed down our search space significantly. Now, back in Mr. Kulik's day, that was a really powerful theorem and very powerful result. But now that you guys have access to a graphing calculator all the time, it's much less interesting of a result for you guys, because the graphing calculator can kind of tell you that instantly. But hey, what if I just took a hammer and smashed your graphing calculator? Then what are you going to do? I mean, you'd be really mad at me for smashing a graphing calculator with a hammer. It seems like that's really uncalled for, Mr. Kulik. What's the deal? What are you so angry about? Well, sometimes I just get angry. You know? All right. So here, this is where we've been heading, right? We have a question asks us to find all the real zeros for some polynomial. Clearly looking at this, there's no greatest common factor. There's no sneaky factoring I can do to do this algebraically. Otherwise, we're going to have to use a lot of piece together some of these ideas that we've had. Since we're looking for zeros, my first step would be to replace f of x with a 0. How many zeros am I looking for? I know there's going to be at most 3 of them. Remember that from last time? So where am I going to start looking I'm going to start looking at my possible rational zeros. So my constant term here is negative 30. My leading coefficient here is 6. My factors of 30, oh no, 1, 2, 3, 5, 6, 10, 15, and 30. Oh, yuckarooskies. My factors of 6 are 1, 2, 3, and 6. Oh dear. So my list of possible rational zeros are going to be every factor of 30 divided by 1, and then divided by 2, and then divided by 3, and then divided by 6. And ay caramba, that's going to be some kind of list there. Hi, Miss
Wow.
Prevert.
Hey, how are you, Mr. Kulik?
Good.
Student in there?
Oh, yep.
Okay.
Katie, it's for yous. All right, well, let's start getting writing then. So plus or minus 1 over 1, 2 over 1, 3 over 1, 5 over 1, 6 over 1, 10 over 1, 15 over 1, 30 over 1. Woo! And now we have to do the same thing. We're going to do 1 over 2, 2 over 2, 3 over 2, 5 over 2, 6 over 2, 10 over 2, 15 over 2, 30 over 2. Huh! Wait a tick. Do you see any redundancies here? Look at 2 over 2. What's that the same as? 1. Don't we already have that on our list? Let's get rid of that. What else do you see that's redundant? 6 over 2, which is just 3. What else? 10 over 2 and 30 over 2. Great. From here on out, let's not write the duplicates if we can help it. So when I write the 1s over 3, I'm just going to write the stuff that isn't a duplicate. So I'm going to skip 3 over 3. I'll put a space there so you can see that I skipped it. I'm going to skip 6 over 3, and skip 15 over 3, and skip 30 over 3. Everybody's okay with me doing that? And then with 6s, same idea. So again, I'm going to skip stuff when I can. 2 over 6 is 1/3, so I don't need to include that. 3 over 6 is 1/2. I don't need to include that. 5 over 6 is unique. 6 over 6 I got. 10 over 6 I have. 15 over 6 I have. 30 over 6 I have. So that's it. That's my list. Ay caramba, Mr. Kulik. What do I got there? 1, 2, 3, 4, 5, 6, 7, 8. And then 4 more is 12, and 4 more is 16. I have 18 possibilities. So these would be and then really times 2 because there's a positive and a negative. So that's 36 possibilities to start my synthetic division with. That's pretty crummy odds because not all of them are going to work. At most 3 of them are going to work. So basically I have a 1 in 12 hat pull. Tell me, Mr. Kulik, please tell me that I can make the odds better than 1 in 12. Because I think that stinks. Don't you? Yeah. Here's how we can improve our odds. I can graph this and take a look. Because what's the same as the zeros on the graph? The x-intercepts. So if I look at my graph, what does this look like? That guy looks like -6. That looks like maybe -0.5. And that one looks like maybe 2.5. Now these ones I'm less sure about because they weren't on a tick mark that I could tell. This one I feel real good about. And if I had a choice to do synthetic division with any of these numbers, which one would we pick? -6. Why? It's a whole number, right? Notice that -6 is on my list. Right there. So I feel real good about starting with that one. So what I have here, 6, 23, -83, -30. I got remainder 0. That's fantastic. So what that tells me then is -6x cubed plus 23x squared minus 83x minus 30 is going to factor to x plus 6 times 6x squared minus 13x minus 5. Whoa, 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 Mr. Kulik. Where did all that stuff come from? Well, that's my dividend. That's my divisor. And that's my quotient, right? Okay, sure. That's fine then. Remember, what did 6x cubed plus 23x squared minus 83x minus 30 equal? In the very beginning, first thing we did was we set it equal to 0. So that factored form is equal to 0. Since I have a linear term, setting that equal to 0 is really easy. I get -6 there. The other piece is quadratic. I know how to solve a quadratic equal to 0. How do you want to solve 6x squared minus 13x minus 5 equal to 0? Quadratic formula, right? So x equals negative of -13 plus or minus -13 squared minus 4 times 6 times -5 all over 2 times 6. So 169 minus 120 is 49. So that square root of 49 is 7. So 13 plus 7 is 20 over 12, which is 5/3. And 13 minus 7 is 6. 6 over 12 is 1/2. So those are my other 2 zeros. And I'm done. Just in time. Cutting it close. At this point, you guys should be able to do up to 43. Woof, Mr. Kulik, that's a lot of problems all of a sudden here. Thanks for dropping that in my lap right before break. Well, here's what I'll do for you. Let's not do this problem check. It'll be due the next one. What's due this weekend? It's what, the 19th or something? Just 1 through 15. How's that sound? Much nicer, right? Okay. Everybody feel pretty okay? Did anybody look at the agenda for Friday on the X day? Homework quiz. What do you think that's going to cover? Just sections 1 and 2. Mostly vocab. Okay. It's mostly vocab. Remember what did we do in like sections 1 and 2? We talked about like what is a zero, what is an extrema. So you might have to look at a graph and pick those off or use your calculator to like find the extremas. It was writing end behaviors using this limit notation. Did we do any math in sections like 6-1? That's really what the quiz is, just these 6-1 ideas. No math, right? Just vocab, understanding what the terminology is, what you're looking for, how to use your calculator to get those things. Should be pretty easy. Then we'll have some Delta Math to work on after the quiz. That's all we're doing on the X day. Sound good to you guys? No? That's what we're doing anyways.